Transient structural analysis is used to calculate stress, strain, and reaction forces. Hello, I'm Armin. In this video, we will learn how to model intermeshing gears using joints and contacts, and how to apply a joint load as an actuator. Before we begin, let me briefly explain the model. Let's get started. Transient structural analysis is a tool for analyzing the motion of a mechanism considering deformation. In other words, the system solves equations of motion that include mass, damping, and stiffness. This method focuses on calculating stress, strain, and the energy stored in components. The solver is implicit, which is more stable than the explicit solver. I will investigate an intermeshing gear system where one gear is rigid and the other is flexible to study stress distribution and joint reaction forces. The geometry is prepared in SolidWorks, and I'll add named selections for the contact regions in SpaceClaim. We'll define frictionless contacts for all the gear teeth and assign a revolute joint to the bore of each gear, allowing rotation around their local z-axis. A joint load with a moment input of 10 Newton meters will act as the driver shaft for the rigid gear in this model. Finally, we'll run the simulation for 0.25 seconds and observe the stress, velocity, and deformation of the flexible gear. That's enough explanation. Let's start the modeling. I want to analyze the gear stress, so we need to use a transient structural system. I'll double-click on it in the toolbox. The first cell is engineering data, where we can create materials or add them from the library. Structural steel is the default material, so I will keep it and close the window. Next, we need to import the geometry. I'll right-click on Geometry and choose Browse. I'll select the geometry file that I created earlier in SolidWorks and then click Open. I want to prepare the geometry in SpaceClaim, so I'll right-click on the geometry cell and select Edit in SpaceClaim. This step can also be done in Discovery. Now we are inside the SpaceClaim module. We can see two identical gears. For clarity, we can rename them. I'll right-click on the first gear in the structure tree, select Rename, and type Gear 1. Then I'll rename the second one to Gear 2. Since these are intermeshing gears, the teeth are in contact. To simplify the contact definition, it's better to name the contact surfaces. I'll select the faces of the gear teeth, go to Selection, and choose Face with Same Area. As you can see, all tooth faces are selected. Then I'll go to Groups and click Create Name Selection and type Contact 1 and press Enter. We also need to add the top land surfaces to Contact 1. I'll select the top land, go to Selection, choose Face with Same Area, then go to Groups and right-click on Contact 1 and click Add. Now all contact faces are fully selected. I will repeat the same steps for the second gear. First, select the tooth faces, go to Selection, select Face with Same Area, then go to Groups and click Create Name Selection and type Contact 2. Next, select the top land surfaces. This time, we can use Face with Same Area or Coaxial Protrusion. Both give the same result. Go to Groups, right-click on Contact 2 and click Add. Now all contact faces for both gears are correctly defined. Everything looks good, so I'll close SpaceClaim. Now it's time to start the modeling, so I will double-click on the Model cell to open ANSYS Mechanical. We are now inside Mechanical. Before starting, let's check the geometry. I will expand the geometry tree, and we can see Gear 1 and Gear 2, which we named earlier in SpaceClaim. The components are flexible by default in the transient structural system, as shown in the stiffness behavior. To reduce the computational cost, I want to set one of the gears to rigid, So I will change the stiffness behavior of Gear 1 from flexible to rigid. Now Gear 1 is rigid, so no volume mesh will be generated on it, while Gear 2 remains flexible. Note that the default material is structural steel, and we can change it from here, but I won't change it. I'll collapse the geometry tree and expand the Connections folder. You will see a question mark beside the connections. I will click on the contact region to see what is happening. As you can see, by default, 4 faces have been selected as contact and target. The contact side is highlighted in yellow, which means the connection is not correct. The contact must be assigned to the less stiff part, and the target must be the stiffer part. Since Gear 1 is rigid, it has higher stiffness compared to Gear 2, so we need to flip the contact and target faces. We can simply right-click on the contact region and select Flip Contact Target. Now the setup is correct, but we still need to select all gear tooth surfaces as contact and target for this connection. How can we do it? It's simple. I will change the scoping method from geometry selection to named selection and select contact 1 as contact and contact 2 as target. As you can see, contact 1 is assigned to the flexible part and contact 2 is the target. One more step remains. In the definition section, the contact type is set to bonded. We need to change it to a frictionless or frictional. In reality, gears have friction between their surfaces, but to reduce computational cost, I will select frictionless. Now we have to define the joints for the bore of each gear. To create a joint, I will select the bore of Gear 2, and from the Connections tab, I'll expand Body Ground and click Revolute. As you can see, Gear 2 only rotates around its local z-axis, and the blue color shows the free degree of freedom. The gear is fixed in all other directions. Next, I will select the bore of Gear 1, and again from Body Ground, I will select a revolute joint. Now both gears rotate around the local z-axis. Let's update the default mesh. I will right-click on Mesh and select Update. As you can see, the flexible gear has a volume mesh, while the rigid gear only has a surface mesh on the teeth because this is the contact region. Let's improve the element size of the contact region. I will use Sizing. I will right-click on Mesh and from the Insert menu, select Sizing. In the scoping method, I will change from Geometry Selection to Named Selection. In Named Selection, I will select Contact 1. A 3 mm element size is enough for this region. I will duplicate the face sizing and change the named selection from Contact 1 to Contact 2. Now I will update the mesh again. As you can see, the mesh size on the gear teeth looks decent. Now let's decrease the element size of the gears a little. The global element size is about 1.7 centimeters. I think 1 centimeter is enough for this simulation. Let's update the mesh. This element size is a little coarse, but it is still good for a tutorial. The mesh and the connections are now well defined. I will collapse the connections and mesh branches and go ahead to define the boundary conditions. We need to add an actuator for the gear. As I said before, Gear 1 is rigid and Gear 2 is flexible. I want to apply an actuator on Gear 1, so I will right-click on Transient and from the Insert menu, select Joint Load. In the Joint Load, I have to select the joint of Gear 1. In the Type options, we can choose Rotation, Velocity, Acceleration, or Moment as the actuator. For this example, I will select Moment. In the Magnitude, we can specify the amplitude of the moment. I will type 10, which is enough for this model. As you can see, the simulation runs from 0 to 1 second. I want the moment to start from 0, so I will change the value at 0 seconds to 0 and press Enter. As you can see, the moment is now 0 at the initial time. But how can we change the simulation time? We can go to the analysis settings, and in the step end time, we can increase or decrease the simulation duration. 1 second is too long for this model because the solve time is more than 1 hour. I'd like to reduce it to 0.25 seconds and press Enter. This is enough because we only need the gear to rotate 1 full turn. In the time step settings, we have to specify the initial, minimum, and maximum time steps. First, I will start with the initial time step. I click on it, type 1e-4 and press Enter. The minimum time step must be smaller, so I will type 1e-6 and press Enter. For the maximum time step, 1e-2 is suitable. The values of maximum, minimum, and initial time steps depend on the rotation speed of the gears. If you use a lower rotation value, you can choose larger time step values for all 3 settings. Everything looks good. Let's check the joint moment. I will click on it, and as you can see, the simulation runs from 0 to 0.25 seconds. Everything looks correct. Let's recheck the model. Gear 1 is rigid. Gear 2 is flexible. The contact between the gears is frictionless. There are 2 revolute joints, and both gears rotate around the z-axis. The mesh looks suitable for our simulation. The time step settings are correct. Everything is ready. I will click Solve and wait for the solution. A warning appears because we only used joints in the model, but it is not important. The solution is complete. Let's go ahead and see the results. I will right-click on Solution, and from the Insert menu, select Total Deformation. Then I will right-click again and select Equivalent, von Mises stress. To see the results, right-click on Solution and select Evaluate All Results. I want to see the gear movement, so I'll click on Total Deformation and play the animation. As you can see, the 2 intermeshing gears are rotating. Now I will click on Equivalent Stress and play it again. The stress concentration is on the gear teeth, as expected. Let's check the velocity of the gears. I will right-click on Solution, and under Deformation, select Total Velocity. Same as before, right-click on Total Velocity and select Evaluate this result. Then let's play the animation. The maximum velocity at the top of the teeth is about 8.81 meters per second. For clearer visualization, we can hide the mesh from the Results tab. Now the visualization looks much cleaner. Let's check the stress again. As you can see, the stress is high at the bore because this is the support region. Now, let's check the reaction force of the flexible Gear 2 joint. I will drag the Gear 2 joint and drop it into this Solution folder. Then I right-click on it and choose Retrieve this result. Now the tabular data shows the total force and the directional forces on the joint. The force components and the total force are listed over time, and the arrow shows the direction of the total force. The implicit solver calculates the proper time step size based on the gear's velocity. The tutorial ends here. Thank you for watching.